Hello and welcome to Physical Sciences, Grade 12 session for Physics, Paper 1. My name is Temba Ngube. Today, our focus will be purely on the mechanics section. But you know, the mechanics obviously has a number of subtopics. But for today, for the purpose of today's session, we shall be looking into work, energy, and power, which is obviously in Paper 1. The physics part. Right, just to quickly get us started, grade 12s, make sure that you have your pen and paper ready, just to, highlight the key things, the main concepts, if you have to take a few quick notes, this needs to be done so that we move together as, the lesson progresses. Now, for the lesson objectives for today, we are going to be looking at work, energy, and power. Now, the first focus area in terms of our lesson objectives is work done, right? So we shall look into what is it that we mean when we talk about work being done on an object by a force. And obviously, there will be those, pre-knowledge aspects that we would have looked at, in terms of grade 10 and 11 work. Now, in grade 11, we have also looked at force diagrams as well as free body diagrams. Now, we remember that when we talk about a force or a free body diagram, there are some similarities and differences in the sense that both of them, they do show exactly, the types of forces that act on an object. But remember, all the forces are applied forces, and the force is always exerted by something on the object. So we concentrate on the object on which work is being done. And then secondly, we shall also do some routine calculations, multi-step problems based on calculation on network, based on the network, which is the total work done. Now, when you look at the word net, it's not entirely for the first time we encounter that term. The word net means total, or it means, the sum. So we're going to add all the forces and get what we would refer to as the resultant force. Right. We will also distinguish, show differences, maybe similarities between positive work as well as negative work done on an object in a particular system. And then we shall also state what the work energy theorem says. Now, remember, when you look at the definitions, they are a pretty much very important aspect of our, our physics topics. All the long questions will start with a definition of some sort. So 2 marks or nothing, we need to keep that in mind as well, right? And then ultimately, we shall apply the work energy theorem to objects moving on a horizontal, vertical, inclined planes in both frictionless and rough surfaces, right? Now, let's quickly look at what we already know as far as some aspects that we've looked at in grade 10 as well as in grade 11. In grade 10, we looked at mechanical energy, which is a combination of both, EMAC, we said, is equals to the sum of the gravitational potential energy plus the kinetic energy. Now, this is energy with respect to, a particular object in a closed system. And also, we looked at, the principle of conservation of mechanical energy. But what comes to mind is the key condition that the system must be isolated or closed, okay? What do we mean by that? We've spoken about a closed system in grade 10. We also say that, if a system is precisely a closed or an isolated system, we are simply saying that the total of the forces that act on that object is equals to 0. So if a system is a closed or an isolated system, the net force acting on that system is equals to 0 newtons. Now, this also, brings something to mind as far as, the Newton's laws. We also looked at Newton's laws in grade 11, where we said that whenever there is a 0 net force on an object, the object maintains its position or it moves, at a constant velocity as a result of a 0 net force acting on it. So that's the Newton's first law, the law of inertia. All those ideas, they do come to mind. And then let's look at what we covered in grade 11. We did a lot on forces, right? And then we also looked at the Newton's laws, including the universal gravitation. But of particular interest to us is the Newton first, okay, as well as the Newton second law as far as work, energy, and power is concerned. Now, the Newton first law, we know that there is a non-zero net force acting on the object, okay? the Newton's first law would definitely be a zero net force, okay? Because the object stays there or it moves with a constant velocity. Now, the implication of Newton's second law is that there is a non-zero net force acting on the object. So meaning that the object will either, actually it will experience an acceleration due to the net force, because we are saying that when a net force acts on an object, the object will accelerate. So the acceleration is essentially a consequence of a net force which is non-zero acting on that particular object. So those are some of the big ideas that must come to mind. We've also touched briefly on force and free body diagrams. But remember as well, when we talk about free body diagrams, we are also, tempted to tap into, the specifics, because all the calculations that will follow, as far as work, energy, and power is concerned, they'll be precisely coming from the free body diagram. Now, the correctness of that free body diagram has a lot of implication in terms of the calculations that we subsequently do. So remember, if a free body diagram, for argument's sake, has got 3 marks, the implication is that there are 3 forces. If there are 4, the free body diagram says 4 marks, it means equally there are 4 forces acting on the object. Right. Now, a brief look into some of the aspects that we have covered in grade 10. We have also looked at the different types of energies, as far as mechanical energy. Now, if we talk of the kinetic energy, we're talking about the energy that an object has due to its state of motion, meaning the faster the object moves, the greater the amount of kinetic energy it possesses. And then when you look at the gravitational potential energy, be mindful of that. When we say gravitational, we're not just saying potential energy, because there are different forms of potential energy. In this case, in the mechanical context, we're talking about the gravitational potential energy. That's the form of energy that an object actually has due to its position above the surface of the Earth. Hence, we call it the gravitational. Right. We also looked at the different laws as far as mechanical energy is concerned. We said E mech, between any 2 points, this was in grade 10, let's say in a closed system between point A and point B, and then E mech at point B. Right. Now, what do we mean? This is the mathematical representation of the principle or the law of conservation of mechanical energy, saying that, a mechanical energy of an object, here we're talking about a single object in a system, which is a closed system. Now, the energy that this object possesses at a given point equals to the energy mechanically at another point, as long as it is within a closed system. But remember, the mechanical energy comprises of the gravitational potential energy as well as the kinetic energy at a particular point. Okay, then this also equates to the gravitational potential energy plus the kinetic energy at a different point, provided the system is a closed system. Right. Okay, then let's look at the key ideas for today. Right. What is it that we mean when we talk about work? Right. The word work, I think, is used in many different contexts in our everyday life. Okay. So when is work done on an object? What does work on an object? These are the key questions or big ideas that we need to ask ourselves. Right. Now, we're saying that the work done on an object must be done by a force. So number 1, work is done on an object. Work is done on an object or a body, right? Work is done on an object by a force, okay? So a force essentially does work on an object, right? Now, we are saying that for work to be done, a force must act on an object. Essentially, we are simply saying, in other words, work is done by a force on an object. So the work done by a force on an object equals the force acting on the object multiplied by the displacement of the object. And then there must be also the direction as far as the displacement of that object is concerned. Now, if you look at the formula, W is equals to F delta X cos theta. Now, this is the work done. That's the work done, okay, by a force, right? And then this is the actual force doing work on the object. So the force is in newtons, right? And then the displacement of the object in the direction of the force is obviously in meters, okay? Now, in grade 10, we looked at vectors and scalars, okay? So if we remember very well, we said displacement is a vector quantity. What does that mean? It means displacement has got both magnitude as well as direction. And then if you look at these two quantities, your force as well as your displacement, these two are vectors. So the product of these two vectors must give us a scalar. Now, what is this theta? This theta is the angle between these two vectors, the force acting on the object and the actual displacement of the object. So theta becomes the angle between the force and the displacement. Okay, so that's the angle, okay, between the force and the displacement acting on the object. Right, okay. Now, we also recognize that indeed work is a scalar quantity. Now, let's talk about the SI unit. Very, very important. Now, if we are to quickly look at a joule of work, because work is measured in joules. 1 joule is equals to 1 Newton meter. Now, we ask ourselves a big question conceptually so that we have a clear understanding of the concept of work. When do we have a joule of work done on an object? Number one, we need to appreciate that what exactly does work on an object is actually a force, right? So when a work of 1 joule is done, what exactly has happened? We have a force of 1 Newton displacing the object in the distance or in the direction of the force, a displacement of 1 meter. So now, in this case, now you'd realize that the force is 1 Newton, and then the displacement is also 1 meter. So a joule equals a Newton meter. Equivalently, when we have, let's say for argument's sake, work done of 100 joules, what does that mean? It means, 100 Newton force, or whatever the product is, let's say it moves 1 meter in the direction of the force. So you'd realize that 100 joules is equivalent to 100 Newton meters. But what is of particular interest to us is that the work done is actually the product of the force and the displacement of the object in the direction of the force. That's very, very important. Right, let's move on to the next slide, okay? When does a force do work on an object? We keep on asking ourselves very, very important question. When does a force do work on an object, right? The first bullet says the force must act on the object in the direction that is parallel to the displacement of the object. There's quite a lot of meaning in that. What does it mean that when we say that the force must act on an object and displace the object in the direction of the force? Right, let's look at a particular example. A block is pulled along a horizontal rough. I'm going to highlight rough. The word rough suggests that there is a frictional force, okay? So it implies that there's a kinetic frictional force provided the object moves, okay? So there's a kinetic frictional force, okay? These are some of the, the key words that we need to highlight as far as problem solving is concerned, right? So there's a constant frictional force acting on the object of magnitude 100 newtons, right? Now, if we look at the object it's resting, and then the 100 Newton force is an applied force that pulls that object in that direction. So for argument's sake, if we were to identify all the forces that do work on the object, we'll have, okay, let's say it's a free body diagram in this case. That's a dot, okay? So the word free body diagram is a diagram that's free of the body. So in other words, we are representing the body with a dot. So the object is represented by a dot there. Now, they've got the 100 Newton force acting in that direction. That's the 100 Newtons, okay? That's the applied force, okay? What else do we have? There's a force exerted by the center of the earth on the object towards the center of the earth, which is the weight. That's our Fg, right? Now, we also have another force, because we're told that this is a rough surface, meaning there is a kinetic frictional force acting on the object of 10 newtons, right? Right. And then also, there is a force exerted by the surface on the object perpendicular to the surface. So that's the description of the force, in other words. So we've got that normal force, which is exerted by the surface of the Earth perpendicular to the surface. Now, the key question is, when is work done on an object? In other words, we want to come to an understanding of these four forces that we have indicated. Which ones of those forces are actually doing work on the object? Right. Now, let's check. We've got the applied force there, okay, which is the 100 newtons. It acts, we assume that the object moves in that direction, right? We assume the object moves in that direction. It's displaced in the direction of 100 newtons. Right. Now, it's very clear for us that, yes, indeed, the applied force displaces the object in the direction of displacement. Right. Now, you'd realize that if we can get another clean sheet, then we've got the 100 newtons, which is the actual force. And then this is the direction of displacement. Right. Now, you'd realize that the applied force as well as the displacement are actually in the same direction. Right. So we are going to say that the work done by the applied force equals to the applied force itself multiplied by the displacement of the object multiplied by the angle between these two vectors. Right. If the displacement is in the direction of the applied force, it simply says to us that the angle between these two vectors is equals to 0 degrees. So when a force does work on an object, in its direction, very important, in its direction, it implies that the angle theta is equals to 0 degrees. Right. So if you go to your calculator, for argument's sake, and do the cosine of 0 degrees, you'll get a positive 1. Right. What does that tell us? It tells us that the work done by the applied force is in the direction of the applied force. Hence, this does what we call positive work. Right. Positive work. Okay. Now, if you look at the frictional force, if you can go back to the previous slide, the frictional force and the displacement are actually in opposite direction. It's actually the kinetic, just to be precise there, okay? Now, if we're going to do a similar thing, we would say, okay, there is the displacement of the object, okay? That's the vector. And then there is the kinetic frictional force. What's so special about the kinetic frictional force is that it always acts in the opposite direction of motion. So if motion is to the right, the frictional force will tend to oppose that motion. Now, grade 9 mathematics, okay, angles at a point on a straight line, they are supplementary. It means the angle between these two is actually 180 degrees. So essentially, what we are saying is that the cosine, which is the angle between these two vectors, the displacement as well as the kinetic friction, the cosine of 180 degrees, if you go to your calculator, it will give you -1. What does this say to us? It says, yes, indeed, the kinetic frictional force does work in the opposite direction of displacement. So this negative has nothing to do with the mathematical number line. It says the direction of work done, okay? Direction of the force doing work. Of the force doing work is actually opposite to the displacement. Is opposite, okay, to the displacement, okay, to the delta x. Very, very important. So if we go back to our main question, when does a force do work? The force must displace the object in the direction parallel to the displacement of the object. But those were not the only forces that we actually identified on the object. If we can quickly go back to the free body diagram, you'd realize that we also have the force due to gravity, okay, the force of gravity as well as the normal force. Now, let's quickly entertain that, you know, if our displacement is in that direction, that's our displacement of the object, that's our normal force, okay? Now, the angle between these two vectors is actually 90 degrees. So cosine of 90 degrees, if you go to your calculator, you actually get 0, okay? Similarly, if we've got the force of gravity, the angle between the displacement is also 90 degrees. Cosine of 90 degrees is actually equals to 0. Now, do these two forces actually do work on the object? Then we go back to our big idea, which says, when does a force do work on the object? Now, as long as the force acts perpendicular to the displacement of the object, that particular force does no work on the object. That's the main idea as far as when is work done on an object. Right. Okay, let's move to the next slide. Okay, now I think the next slide kind of summarizes the discussion that we've just had. A force that does positive work, it is the force that does work in the direction of displacement, and the angle between the force acting on the object and the displacement is 0. And then if they are opposite, the angle between them is 180. That particular force does what we refer to as negative work. And then a force that does no work must act perpendicular to the displacement. So in summary, what we are saying as far as no work done by a force acting on perpendicular to the object, a force that acts perpendicular, perpendicular geometrically, obviously it will say it's at an angle of 90 degrees. That acts perpendicular to the displacement of the object does no work. So this should be quite emphasized at this point. So a force which acts at 90 degrees to the displacement or the movement of the object, that particular force does no work on the object. Right. Let's move to the next slide. Now, we also spoke about determining total work. Right. I think this is the most important aspect of our problem solving. But the procedure or the sequence of steps that we take as far as solving problems that have got to do with routine calculations is very important. The data sheet is something that cannot be overemphasized. Now we know that it's very, very important. The formula is given. Right? Now, here's a scenario just to get us, to give us a picture of what exactly it entails when you're given a scenario to determine the total work. Now, the word total means net. It also means sum, which means we are adding, right? But remember, we're not just adding here. We are talking about vectors, okay? Vectors, it could be in terms of forces acting on the object, right? On object, meaning the moment we start talking vectors, then direction becomes of particular interest to us, right? A crate of mass 30 kg is pulled, meaning the moment we say pull, it means that a force is applied, onto the object of concern to us, and then along a rough horizontal surface. Now we have also highlighted that when it says rough, the implication we know from grade 11, it means there is frictional force, okay? There is a frictional force acting on the object, and we assume that that force is actually constant. And then we're told that the force that is acting on the object is 50 newtons, and it acts at an angle. Wait a minute. Now, this is the angle at which the applied force acts on the object to the horizontal. Now, a frictional force of 20 newtons acts on the object. Now, kinetic frictional force given to us is 20 newtons. Take that into account as well. Now, this is the procedure generally as far as determining total work. We want to identify all the forces acting on the object, on the crate, okay? Now, a free body diagram, it could be a force diagram. Careful of the differences between the two, right? Okay, so in this case, we'll choose a free body diagram because it's the most common one. Now, we've got the applied force of 50 newtons at an angle of what? 30 degrees to the horizontal. That's the force of 50 newtons. What else do we have? We're told that this is a rough surface. So meaning that there is a kinetic frictional force acting on the object of 20 newtons, right? We can label it Fk for now, it's fine. What else do we have? Okay, we've got the weight of the object, which is exerted by the center of the earth towards the object, towards the center, on the object, towards the center of the earth. Then that's our force of gravity, right? And then we also have the normal force, right? That's the normal force. So that's our free body diagram, basically, of all the forces. Now, the next piece of the puzzle that we need to, kind of put together is, I ask ourselves, which of the forces are actually doing work on the object? Now, we know there is positive work, there is also negative work, and also there are forces that don't do any work. Now, this object, the assumption is that it moves horizontal. Now, of interest to us now is this 50 Newton force, which acts at an angle. If we can go back to what we already know, we know that the 50 newtons, okay, which is, let me put it in broken line there, that's the 50 newtons, which is the applied force, consists of a horizontal component, which we can call Fx, and also a vertical component, which we can call Fy, right? Then obviously, if we choose the components, these two components, they obviously represents the 50 newtons. Now we can remove this one. We can remove the other force. So because the components represent that particular force. Now we know that Fx from our grade 11 is actually F applied cosine of theta from our trig ratios, okay? And then Fy becomes F applied sine of theta. These from the trig ratios that we know from grade 10 and 11. And these formulae, I must indicate, they are not given, right? Now, if these are the forces, okay, in terms of the applied force, then we also have the other forces, which is the normal force, okay? We also have the kinetic frictional force, and then we also have the Fg. Now, which of the forces are actually doing work on the object? We know this one does negative work, that does positive work because it's in the direction of displacement. So these forces, they don't do work on the object, right? So if that's the case, then we are left with a scenario of this sort, okay? We've got the Fx, which is 50 cosine of 30 degrees, right? Then we also have the 20 newtons, right? Okay? Now, these are the two forces that actually do work on the object because the displacement of the object is actually horizontal in that direction, right? Now, we want to determine the total work, right? So the total work done is equal to actually the work done by Fx plus the work done by F kinetic, right? So this is the net in terms of the total or the sum of the forces. Now, work net reduces to, in this case, Fx, we have to determine Fx. So that's our 50 cosine of 30, right, degrees, okay? So this is actually the magnitude of Fx. The displacement is actually given, it's 6 meters, right? Then cosine, this is the angle between Fx and the displacement, which is equal to 0, plus for the net, and then we've got 20, which is the kinetic frictional force, multiplied by the 6 meters, which is the displacement. In which direction is the frictional force? It's obviously opposite of the displacement. Then the angle between those two vectors is 180 degrees, right? Then from our calculator, we are then able to determine the value there. So first of all, let's try and simplify that F50 cos 30 degrees, which is our Fx, right? So if you go to your calculator, it will say 50 cosine of 30. It gives us 43,3, right? 43, that's the horizontal component, comma 3 multiplied, okay? 43,3 multiplied by 6 multiplied by positive 1, okay? This gives us 259. Okay, this is the work done by the F horizontal, comma 81, okay? 2 decimal places. And then plus, okay, the work done by the frictional force, this reduces to -1. So this is going to be -120, right? Be careful. is the sum for the net, and then this is the direction. The negative suggests the direction of the work done by the kinetic friction. So if you say that minus 120 is going to give us 139, comma, okay, it's going to be 139, comma, 81 joules, okay? Take note, this is the total work that is done on the object by those forces that actually do work on the object. I think that was pretty much, you know, a simple case, right? And then if we go to the next one, what exactly does it entail when we determine the total work or the net work? Number one, we must be able to draw the free body diagram and showing all the forces. Subsequent to that, we must also be able to identify the forces that actually do work. Then also the angle theta in terms of the work formula is the angle between the force doing work and the displacement of the object, okay? Right, now we can also calculate the total work by adding the actual work done by the forces that actually do work on the object. Alternatively, we can simply go back and say, okay, the work net, okay, is equals to F net, because total work is done by the total force, delta x cosine of what? Of theta. Now, if you look at that formula, it says the total work is done by the total force. So from our free body diagram, we had that 50 cos 30 degrees, which is our Fx, and we also had Fx, which is 20 newtons, okay? F kinetic, which is 20 newtons. Now, if we're going to determine the net force here, F net is equals to Fx plus F kinetic, right? Now, if we have our Fx, which is 50 cos 30, we managed to do that earlier on. It gives us 43,3, okay? 43,3 plus negative 20. What does the negative suggest? It tells us that the frictional force acts in the opposite direction of the horizontal component of the applied force. So this is going to give us what? 23,3 newtons, because this is the net force. Then work done by the net force becomes 23,3, which is the actual net force, okay, multiplied by the 6 meters cosine of 0 degrees. Why did we choose 0? The 23,3 newtons is in the direction of displacement. Very, very important. Right, so if you do that 23,3 multiplied by 6, it will give us exactly the same answer as the one that we did times 6. It gives us 139,8, which is the actual work done by the net force. So very, very important. So if we go back, I think also the calculate this, the 139,81, that's what we got. So this actually is exactly the same as the one that we got in the work done by the net force. Okay, so but those are just routine calculations. And then quickly to look at the next slide. Okay. Right, we've done that. Okay, multiple choice. Right, it's another very, very important aspect of our paper 1 physics. It's also applicable in the chemistry. So the skill involved in the multiple choice, it needs a lot of practice. It needs a lot of work. And if you think of the multiple choice, it's actually 20 marks. Very few of the questions in section B are worth 20 marks. It means if question 1 is 20 marks, you need to allocate sufficient time for you to actually get those 20 marks. And the technique of responding to multiple choice question is one area that needs a lot of work, because there's this conception that the multiple choice questions are actually straightforward. You may find that in most cases it's actually not. It needs a lot of thinking. It needs a lot of conceptual understanding. Let's look at this example, just to get us through the technique. The kinetic energy of a car moving at constant speed is V. Speed V is equals to EK. And the speed of the car changes to half V. Okay? Now, whatever speed it was, now it's half the initial speed. what is the new kinetic energy? Now, this question actually tests our conceptual understanding. Now, much as work energy theorem is about work, but there is an aspect of energy that is also very important. Now, what do we know? We know that EK is equals to half mv squared, right? Just to wrap it up, we are saying that this is EK, right? When the speed is v, the kinetic energy is EK. What if we change the speed v to half v? What are we going to have? We're going to have half the mass. What's the new speed? Is v over 2, which is half, okay? But we're going to square that. Now, this gives us what? Half m, v squared over 4, okay? Which is the same as half m v squared multiplied by 1 over 4. Now, what did we say? Half mv squared equals to EK. Now, that's our EK multiplied by a quarter. So our new kinetic energy will be equals to EK multiplied by 1/4, or in other words, it can be EK over 4, right? So this is a skill that you need to, kind of master as far as, solving, the multiple choice question. And the key questions that you need to ask yourself is whether, if we have the speed, does the kinetic energy increase, decrease, or remain the same? So if you look at C and D, they say that, the speed has, the kinetic energy has increased. It means C and D are distractors. So our answer is between A and B, which says decrease. But the actual one is 1/4 EK. It means the answer is A. So these are some of the little things that you need to kind of, familiarize yourself and also use the data sheet accordingly. Then as far as, the basics of what it entails as far as work energy power is what we've just discussed, and I've managed to, kind of take you through it. But there is quite a lot beyond just these concepts, which needs, your careful attention. From myself, Themba Ncube, is cheers and bye-bye for now.